So I'm a macroeconomist who works on economic growth my whole life, and this is my perspective on where we've come from and where we might be going. This is a chart of average income per person in the United States over the last 150 years. And the stunning thing about this fact is that it adheres so closely to a line with a slope of 2%, right? So living standards in the United States on average have grown at 2% per year, plus or minus something, for 150 years, right? So what you should be thinking in the back of your mind is, wow, a lot of things changed over this period. Electricity, the rise of education, globalization, and yet 2%. Okay, so a big part of the growth literature is concerned with how do we understand this fact at all? Where does growth come from? So I want to start with that, and then we'll get to what the future might bring. Okay, so the theory of economic growth relies really heavily on this wonderful research by Paul Romer, who won the Nobel Prize 6 years ago. And the key to his contribution is that ideas are special. Ideas are different from every other good that you're used to thinking about. He called them non-rival. I don't like that word. I prefer infinitely usable. Right? So think about standard goods. This computer, a barrel of oil, an hour of a surgeon's time. All those goods are rival in the sense that if I'm using it, you can't use it. Right? Ideas are fundamentally different. Think of calculus, the design of the mRNA vaccine for COVID, the latest machine learning algorithm. You invent it once, and then it can be used by any number of people simultaneously to expand their productivity or increase their utility, right? And it's that sort of infinite usability of ideas that's the key to understanding this picture, actually. Okay, and one way to see that, I think the simplest summary here, if you want to make a worker more productive, you can give them a computer. If you want to make 1,000 workers more productive, you need 1,000 computers. Or you can give any number of people one new idea. You invent electricity, and it can make billions of people better off, right? And it's that infinite usability character of the idea that does that. And so kind of at the bottom of the screen here, the way these models work, it says income per person is determined by the total number of ideas we've ever discovered and put in place and everything Eli was talking about. Where do those ideas come from? They come from people, at least currently. I'll come back to AI on my last slide. People create ideas. Those ideas are infinitely usable. That raises everyone's living standard. Okay, that's the way these models work. An interesting implication of that theory is look at the first part and the last part. Income per person is tied to the number of people. It means the growth rate of income per person is ultimately pinned down by the growth rate in the number of people looking for ideas. And the number of people looking for ideas, the growth rate of that can't be any higher than the population growth rate in the long run. And so kind of surprisingly, the growth rate of living standards is determined in the long run by the population growth rate. The growth rate of people, which in turn determines the growth rate of people looking for ideas. So population growth is the key to long run economic growth. And in the long run is doing a lot of work, as I'll show you in a couple of slides. Okay, so what I want to do for the remainder of my time is talk about the future of growth. And I'll highlight some headwinds that might, lead growth to slow down, and some tailwinds that might lead growth not to slow down or maybe even speed up. And I kind of want to lay out different things here. And this is where we'll talk about ideas getting harder to find. Before I get there, there's a question in the previous session about, all the free goods, Facebook, Google search, and free is in quotes there. We pay for those. Those people get paid. So, people are getting paid. But how much of the growth slowdown is due to, it's just measurement. I liked Eli's answer to that. There was lots of measurement error in the past as well. Another answer that I like a lot is to look at the manufacturing sector. The manufacturing sector doesn't have a lot of free goods. It's not contaminated that well. It's viewed as the sector where we measure things best. Okay, it was the sector that historically grew very rapidly. But, and this is just a stunning fact, I kind of wouldn't believe it, but it's what the data says, so we have to confront it. Since 2005, the level of productivity in manufacturing is flat. Kind of zero growth since 2005 in the sector that was very fast growing before that, in the sector that's well measured. So this slowdown in growth is a real thing we have to confront. Eli kind of dated it back to 1973. I think if you wanted to make a more nuanced take, you'd say 73 to the 90s was a slow period. 95 to 2005 was a really fast period. If you looked at his graph, we were back to the parallel trend. And then post 2005, post 2003, a big slowdown again. And that, I think, has something to say about the regulatory angle. It wasn't that everything slowed down in 73 and it never sped up again. We did have this resurgence of growth in the late 90s, the dot-com boom, the new economy, et cetera. Okay, so the slowdown's a real thing, and we're worried about it. We'd love to understand it better. This brings us to our ideas getting harder to find. Importantly, and this, I kind of can't emphasize this enough, our paper, I love our paper. I love the title for our paper. It got way more attention than it deserves. Our paper says nothing, it's not quite true, but it says nothing about this slowdown. I'm going to claim ideas are getting harder to find, but they've always been getting harder to find. Are they increasingly hard to find? I don't know. That's hard to tease out of the data. Okay, so this slowdown in 2005, I don't know what the answer is. Okay, but I think it's still the case. Ideas are getting harder to find. They've always been getting harder to find, and that has really important implications for the future of growth. That's the argument I want to make here. So how do we make that argument? All of these growth models have at their heart a production function for ideas, where people produce ideas and those ideas lead to growth. That's the channel we talked about before. So here's my sort of simple version of the idea production function. There's research effort on the right-hand side, and research effort gets multiplied by the productivity of researchers. Right? How many ideas does each researcher produce? And that gives us a total number of ideas on the left-hand side. Now, actually, I don't have total number of ideas on the left-hand side, kind of for an obvious reason when you think about it. Measuring ideas is really hard, and ideas are incredibly heterogeneous. 99% of ideas aren't worth very much. 1% of ideas are worth a lot. And even within the 1%, some of the top ideas are worth way more. So how do you add up ideas in a way that you could use this idea production function? That's a really, really hard question that the direct approach doesn't have great answers. So what economists do is use an indirect approach, which, remember I said, the advantage of ideas is it throws off this economic growth. This is the source of economic growth. We measure growth pretty well. Growth is in units, productivity growth, that we care about, that kind of appropriately weights each ideas. If the ideas are small, they have a small effect on productivity growth. If ideas are big, they have a big effect on productivity growth. So using growth as our measure of ideas is what this literature does. Okay, so growth is measured reasonably well, say 2% for 150 years, that number I showed you just as an example. Research effort, we can also, with some work, measure. And so what we're going to do is measure research productivity as the residual in this equation. So we measure the left-hand side well, we measure research effort well, divide them to get a measure of research productivity. Okay? When you do that, what do you see? Well, 2% growth for 150 years, pretty stable, for example. That's what you saw. Research effort in the US economy for the last century, risen by a ton, right? A factor of more than 20, maybe a factor of 25. We're doing a lot more research today than we were 100 years ago. And so that must mean, as a matter of this identity, that research productivity is falling by a factor of 20 or 25. So research productivity is falling, and yet the benefits to doing that research are getting larger, right? So it's getting harder and harder to push Moore's law forward. But if you push Moore's law forward, you can sell it to the whole world economy, and that makes it worth it. And in some sense, those two things hang together. So I kind of connected it to the aggregate data that I showed you already. My favorite example, what we do in this paper is we look at 5 different sets of examples, kind of case studies. My favorite one is Moore's law. Right? So Moore's law is driving a huge amount of the growth. You saw it on Eli's chart. The productivity growth in compute is just, dominates the rest of the economy. So Moore's law, remember, the density of computer chips doubling every 2 years for 50 years, right? That's constant exponential growth at a rate of 35% per year, rule of 70, right? Constant exponential growth, that's the straight line you see on the charts of Moore's law, kind of like the straight line I showed you in the first graph. Okay, so economic growth is constant. The left-hand side of this equation is a constant at 35% per year. What about research efforts? So there we had to spend some time measuring how much R&D is done to push Moore's law forward by Intel and TSMC and ASML and Samsung today, and then go back historically and look at AT&T and Texas Instruments and IBM in the 1980s, and go back to National Semiconductor and Fairchild in the 1970s, try to parse that out. It's a hard problem. We do it 6 different ways to show you what we find. What you see everywhere is research effort towards pushing Moore's law forward is rising enormously. In other words, this is 18 times higher today than it was in the 1970s, and therefore, as a matter of accounting, research productivity has fallen by a factor of 18. It takes 18 times more research effort today in the 2010s to generate that doubling of chip density than it did in the 1970s. We basically need to measure the left-hand side in that research effort, and we tried to do it everywhere we could get good data. Okay, so we did it for Moore's law, we did it for the aggregate economy, we did it for cotton, wheat, corn, and soybean productivity in agriculture. We did it for health innovation, so the drug discovery number that Eli showed, but also mortality related to heart disease and cancer and breast cancer. We did it for firm level data. Everywhere we looked, you see this picture. Now, venture capital, we didn't feel like we had the right data for it, but we would love for people to do this with more examples. In some ways, one way to think about it is suppose AI can substitute for research effort, then this equation might be off. This equation does work if you have sort of labs that use capital to help produce ideas. That's in the model buried there. So what we find everywhere we look, and we haven't looked everywhere, but we looked at a bunch of places, is what I said. Growth relatively stable, maybe even declining. Research effort rising like crazy. And so as a matter of accounting, research productivity is falling. Now, what's the explanation? Why is research productivity falling? It could be that at a technological level, ideas are getting harder to find. It's part of the technology. You get the low-hanging fruit. I actually think that's probably true. I think for Moore's law, that is true. But it could be other things. So your sloppy science is one. Eli's, regulation, right? There are more and more regulation. Notice you need increasing regulations. Regulations are increasingly hitting things in a way that drives research productivity down. Now, I think, again, for Moore's law, I think that's not it. So I do think this idea is getting harder to find technologically is probably part of the story. But our finding just says research productivity is falling. We don't say why it's falling. And I think these other explanations, you kind of want to explore those carefully. And what Eli and other people are doing, I think, is kind of great on that front. So here's the number of new ideas, and new ideas feed into productivity the way Romer taught us, right? This is research effort. For this research productivity, you can measure it as the stock of knowledge to some negative power, okay? And then now you can see why, okay, if the growth rate of knowledge is constant, it has to be that research effort and the stock of knowledge raised to some power, exactly offset. That happens endogenously. That it's not a magic thing. It's the stable differential equation that converges to that situation. So it does hang together, but I'm not showing you the model. I think this last bullet point is sort of helpful for putting together the 2 things I've showed you so far. I think of this model as kind of the Red Queen theory of growth. You have to run faster and faster and faster to stay in the same place. We have to throw ever-increasing quantities of researchers at these problems in order to maintain 2% growth. An implication is if we ever stop running as fast as we were, growth can slow down. Okay? So let me show you, what does it look like? Are we running as fast as we used to? And this is a tricky question because, productivity growth in the US benefits from ideas created in Japan and the EU. So in some sense, it's a world R&D stock appropriately weighted for the diffusion of ideas that you want to put. I don't have that appropriately weighted diffusion of ideas is hard. So what I'm showing you here is just research employment in the EU, the US, and Japan. And what you see is sometime around the early 2000s, the growth rate of research employment slows in all 3 of these regions. Okay? Now, if you fed that through my model, it would predict that growth rates should slow. The magnitude's not going to work out to be nearly the same as the slowdown, but this is an example of how we may not be running as fast as we used to. Now, you could easily say, what about China doing a lot more research? How does that all get added together? It's a really interesting question. I wish I knew how to add them all together. So this is why this is just sort of a useful data point to keep in the back of your head, but I don't think it nails the question at all. Another fact I want to show you that I find fascinating, this is just from the National Income and Products accounts. National Income and Products Accounts keeps track of how much investment are we doing in different goods. The goods here are the investment in the infinitely usable ideas, right? So R&D is clearly investment in ideas, but software and entertainment, software is ones and zeros. It's also infinitely usable. It's non-rival as well. So when you add up software and entertainment, government-funded R&D, privately funded R&D, here's what the National Income and Products Account says for the share of GDP. So remember, I told you research is growing like crazy. It turns out, like measured in bodies, even measured as a share of GDP, investment in infinitely usable ideas has been growing like crazy. In the 1930s, it was 1% of GDP. The latest data says it's 6.5% of GDP. Okay, so again, growth rate 2% per year for 150 years. We're investing ever larger fractions of GDP in making that happen. So it could be that the regulatory barriers are just offsetting. This to me would be magic because there's not an endogenous reason why that would happen. But we are throwing tons and tons of resources at these problems and only maintaining 2% growth. Another interesting thing here, government R&D versus private R&D, you could see like an interesting change in the composition, right? In the 1960s, government R&D was kind of half of investment in infinitely usable stuff. Today, government investment's kind of maybe 15% of investment in infinitely usable stuff. The sum of private and government for the last, 40 years has been pretty stable, actually increased in the last, maybe 5 or 10 years. But the composition has changed dramatically. We're doing way more private R&D. Private R&D as a share of GDP, up, 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 up. Firms are doing their part. Evidently, they're getting returns for it. They're not doing it for free. Could be relabeling. I don't think this kind of magnitude is relabeling. Government doing less and less. There are two views you could have on this, and I don't have a strong evidence or prior about which it is. On the one hand, economists tend to like it when the private sector does more. If the private sector can do it, let the private sector do it. That would say this could be good. On the other hand, to the extent that you think it's a pipeline model, that the government funds the basic research and the private sector commercializes it, then you might be worried by this large decline in maybe basic research, right? And I think that's a candidate explanation for some of the slowdown, but only a speculative candidate explanation. So what I've said so far, I've tried to convince you that in the long run, all of growth in living standards is due to population growth. You may not believe that. That's kind of what the model says, so it's an interesting finding. What I want to say now is let me do some growth accounting for the last 75 years. How much of growth is due to population growth? How much of growth is due to other things? I'm doing the growth accounting in my framework. So in my framework, all of growth in the long run is due to population growth. But for example, rising R&D as a share of GDP is going to generate some transitory increases in growth rates. And this share cannot rise forever. It's a share. It's bounded at 100%. So someday this share has to level off. When this share levels off, growth will presumably slow. Okay, so the accounting is the way to see that. So here's this is kind of a stylized accounting. I'll show you why I use the word stylized in a second. 2% growth, say 1950s to today. The capital output ratio, nothing. Investment in capital is pretty stable, right? So there's kind of, the way I do the accounting, there's nothing there. Human capital per person, educational attainment, fully a quarter of our 2% growth. So the 20th century is the century of expanding educational attainment. Educational attainment rises by just under a year per decade. Labor economists tell us that each year of education raises wages and hence labor productivity by, say, 6 or 7%. So a year per decade, 6% per decade, it's a little less, so call it 5% per decade. That's 0.5% per year. That's this quarter of growth due to rising educational attainment. It can't, if you think about it, it's what fraction of your lifetime do you spend in school? That can't rise forever either. In fact, educational attainment already in the late 80s and 90s is leveling off. We're not seeing the same 1 year per decade that we saw from 1900 to 1980. And so this 0.5% per year of growth is disappearing. Okay, it's unlikely to be there in the future, and you can already see it going away. Employment population ratio is a similar story. The rise of female labor force participation. Women entering the labor market, great thing. If more people are working, that raises per capita income, right? So that's about 0.2 percentage points. That also can't go on forever, and it's already leveled off, right? By around the year 2000, women's labor force participation had flattened out. So that 0.2 is not going to be there in the future. That leaves us with 1.3% TFP growth. And then let me decompose the TFP growth into R&D intensity. That's like the R&D share of GDP. And then population growth, and then this misallocation term that I'll come back to in a second. So R&D intensity, I showed you R&D as a share of GDP rising like crazy. That's 0.7 percentage points of growth. That again can't go on forever. The share has to level off, so that's going to go away. Misallocation is kind of what Eli was talking about. The term I would use for Eli's regulation or inefficient allocation of resources, we call that misallocation. So I'm going to show you on the next slide a story for how declining misallocation might contribute 0.3 percentage points to growth. But it's stylized because this is just one story, and I'm not measuring, all the things that Eli wanted me to measure. So I'm leaving out some things in just 1 second. And so that leaves the remainder is population growth, but that's only 0.3 percentage points of growth, only 15%. So even in my worldview, where all of growth in the long run is due to population growth, over the last 75 years, 85% of growth was due to other things. That's good and bad. The bad news is all those things are going away and growth would slow. Oh, and by the way, population growth rates are slowing. Fertility rates are below replacement. This term may be zero someday. So there's a lot in this graph that points to, wow, we might be pessimistic about growth in the future. Okay, misallocation story. What's happening to the efficiency of resource allocation in the United States? There are a bunch of stories one could tell here. I'm going to we measure one of them in this paper. So we're not measuring all the other ones, but this one I think is interesting and telling. So this is the Sandra Day O'Connor story. Sandra Day O'Connor, first woman Supreme Court Justice in the United States, graduates third in her class from Stanford Law School in 1952. So clearly superstar talent, future Supreme Court Justice. The only job she could get from the private sector is as a legal secretary. Okay, that's the misallocation of talent, right? There's this talented person who, because of various barriers and discrimination, can't get the job where her talents kind of suggest she should be working. Of course, that story applies writ large across the entire US economy. These facts, you kind of know them, but I was stunned when we put them together. I mean, it's easy to forget, and that's probably a sign of how much progress we've made. White men in US business in 1960, 94% of doctors, lawyers, and managers. 50 years later in 2010, 60%, right? So this is kind of the Sandra Day O'Connors coming into their own and starting to become doctors, lawyers, managers, and other sort of high-skilled professionals. So this paper is a growth paper. The question we ask is, how much of that 2% growth can be explained by this improvement in the allocation of talent? Okay, and it turns out to be surprisingly large. So 40% of growth in GDP per person. A lot of this is female labor force participation. So women who used to be at home because they couldn't, get paid for their talents in the market, increasingly getting paid for their talents, so entering the labor force, and then 20% of growth in GDP per worker. So this is just evidence supporting what Eli was saying is there's a lot of changes in the allocation of resources, in misallocation. This one went in the positive direction. There may be others that go in the negative direction, but at least here's one that went in the positive direction. Paying attention to the allocation of resources, a huge deal. That's kind of what this paper suggests. So on this misallocation point more broadly, so I've given you the headwinds, a lot of reasons to be pessimistic about growth in the future. I want to give you some reasons to be less pessimistic, maybe even optimistic, right? So China and India, right? In 1980, China and India are so far below the frontier, so poor, not getting the education that you need to push the frontier forward. Each of China and India is as populous as the US, Western Europe, and Japan put together. So there are a ton of people in China and India that as China gets, grows fast, gets more educated, starts engaging in research and patenting and pushing the idea frontier forward in, solar cells, for example, or AI as well, that's another billion people we can throw at these hard problems. So we may be running out of people for lots of reasons, but this composition effect of bringing China online, bringing India online, gives us a lot more people to throw at these problems. And that's potentially a reason for optimism on the growth side. The misallocation point, again, how many Steve Jobs and Jennifer Doudnas are there that we're missing out on because, say, they were poor when they were growing up and didn't get the opportunity? So the Tyler and Patrick's work on talent and how to take advantage of talent and how to find the talent, absolutely hugely important thing. And then finally, I want to go to AI, which is my last slide. One of the topics I've been working on a little bit over the last 5 years, and that it's kind of my next research project, is to think more about AI and economic growth, but just sort of to give you two different points of view here. And maybe I'll say what I think of each of them as we go through. The growth models that are kind of the state-of-the-art models where people produce ideas, and therefore the growth rate of the economy is limited by the growth rate of the number of people. Well, what if machines can substitute for people and produce ideas, right? AlphaFold and then GPT-5 and GPT-6, what happens there? It's actually theoretically possible in a mathematical sense to get explosive growth in a singularity. We could reach infinite income in finite time. That's a possibility. The way it works is if machines can do everything people can do, then machines can produce ideas. That gives us more ideas, more output, more machines, then more machines to throw at ideas, and there's kind of a virtuous circle there. Romer's non-rivalry, his infinite usability, means the economy is characterized by increasing returns. Virtuous circle plus increasing returns equals explosion, okay? I don't want to claim it's incredibly likely, but in my worldview, it's kind of hard to raise the growth rate. And it's interesting that AI producing ideas is absolutely something that could contribute to raising the growth rate. And one of the things I want to work on is kind of put some numbers on that in a step-by-step fashion in the future. Okay, so it's absolutely possible that growth rates could be higher. On the other side, history suggests caution, right? So economists have studied the adoption of the steam engine, electricity, computers. We talked about the computers showing the Solow paradox, not showing up in the statistics for a long time. My version of that is automation's been going on for 200 years. The Industrial Revolution is automation, using textile looms, capital to replace labor. Automation's been going on for 200 years, and yet 150 years of stable growth. Similarly, if you think about the ideas that were created over that 150 years, the steam engine, electricity, internal combustion, semiconductors, fantastic transformational general purpose technologies. And yet, even with all those things, 2% growth. Okay, so one way to interpret that is not that general purpose technologies don't matter. That would be the wrong interpretation. The right interpretation, I think, is, okay, maybe within each general purpose technology, you get it. And when you first get it, there are all sorts of great things to do. That's what we're seeing in biotech today, is my interpretation of Eli's evidence. But as time goes on, ideas get harder to find in each general purpose technology. And so growth slows down. And then it turned out we discovered the next GPT and the next GPT and the next one. And that is kind of magical that it happened to balance out. It doesn't have to at all. But if you want to understand the facts, that's at least one story that makes sense of it. So in that telling, maybe AI is just the latest great idea that prevents growth from slowing down and allows us to maintain 2% growth for another 50 years. Or it could be 1% growth for another 50 years, or it could be 3% or 5% growth for another 50 years. But you sort of see this is at least one way of putting together the history in a way that that kind of makes sense. So let me stop there. I put some QR codes if you want to see the slides, some of the graphs, or other things I've worked on my webpage. But thank you very much.